So for these last 2 weeks of Physics 30, we are going to be looking at the evolution of the atomic model. In this process, we are going to revisit some of the ideas throughout the course. But our goal is to understand where we started, where we've come with the atomic model, and why these models had to change, and how they've changed over time. So we start with this billiard ball model. Cathode rays led to the idea that these electrons could be broken off. So the atom went from being indivisible to divisible. We could actually divide it, and we had these negative charges. Then we did the gold foil experiment, and we found evidence that the nucleus was a space of dense positive charge. That led to this planetary model, or the Rutherford nuclear model, where we had a region of dense positive charge. But we know that accelerating charge produces EMR. And that led us to Bohrs Model, where these regions, there were specific distances from the atom where these electrons could exist and be stable. That was the Bohr model. Now, if we think about the Bohr model, there's still no explanation why these electrons are stable. And that's what we're going to get into next week. But this week, we'll be dealing with questions that involve cathode ray tubes all the way to energy changes, emission spectrum, absorption spectrum, and the like. So we're going to start with early theories about atoms, and this is the 1800s. Now, there were earlier ideas in like ancient Greece where they talked about, well, stuff had to be made up of things that were smaller. But kind of the first kind of modern ideas of the atom came with John Dalton. And so his model was the solid sphere model. So he took these atoms and he said, using chemical ideas, he knew that every atom had a different mass. And he knew that things went together in whole number ratios. So he came up with the idea that every atom could be expressed as a solid sphere. And different atoms were different spheres, but we could break them down to that form. That's kind of where we're going to start. Now, the next step happened with the discovery of cathode rays. This is a Crookes tube. So there is this tube, and you can see there's a cross in it, and then there's a shadow on the other side. So we observe a shadow, and from that, we can infer that there are moving charges, or charges can be separated. So there are we can infer a separation of charge. Or there's something moving, and we know which direction that it's moving. So we have the anode and the cathode, and so we're able to determine that they're charged particles and which direction they're moving, that they're going from the negative, in this case cathode, to the anode, is what we can observe. So that's the Crookes tube, and that's kind of where we started. Now, the first scientist we need to know, so Crookes kind of made this tube. So J.J. Thompson used this idea, and he developed on it, and he ended up winning a Nobel Prize, and there was a lot of other famous scientists that came along that worked for J.J. Thompson. But J.J. Thompson's where we're going to start, and that's J.J. Thompson's cathode ray tube. Now, he did a couple of experiments. First, he wanted to see if the negative charges could be separated from the cathode rays. So he took a cathode ray, so it's going here. So there's this greenish glowing ray that goes through that tube when he turns it on and puts a high voltage through it. And he would bring a magnet up to it. And he saw that as this magnet was brought up to it, it was deflected as it would if it were a negative particle. And we can kind of think about that kind of using our hand rules, which direction that it should go. Now, it deflected like it was all negative charges. So it wasn't just negative and positive charges combined. Those cathode rays would deflect like they were negative charges only. And he found that they also deflected in an electric field, as negative charges would be expected to actually be deflected. So they knew that these rays were actually negative charges. So it was actually the first evidence of the electron. Now, we hadn't seen electrons before, so this was kind of groundbreaking that we could actually separate positive, negative charges. We knew we kind of could with static electricity, but we didn't know that it was those negative electrons which were present in the cathode ray tube. The other thing that J.J. Thompson found was the charge to mass ratio. If you think about the charge of an electron to its mass, that's what the charge to mass ratio is. And he did that using this cathode ray tube. So this is a cathode ray tube, and it's kind of modified. It has an electric field and a magnetic field that can be manipulated. And let's kind of look at what's going on. So we have this electron. So these are our cathode rays. They're coming through this region here. And in this region, we have two different fields. We have an electric field and we have a magnetic field. If the electric field is only turned on, so if there is only an electric force acting on these electrons, it's deflected and it hits the top. If we turn off that electric field and turn on the magnetic field, so if we use our left hand, our thumbs are going to the right, fingers into the page, the magnetic force is down. If there is only a magnetic force acting on that, acting on the object, it will be deflected down. So we know that. So we know it's deflected up, it's only an electric field. Deflected down, it's only a magnetic field. Now, if we manipulate both of them so those electrons pass through undeflected, then we know that the electric force up is equal to the magnetic force down. Those forces are equal and opposite. So the electric force is equal to the magnetic force. Now this allows us to derive what's called the velocity selector formula. So my electric force can be calculated with EQ, and my magnetic force can be calculated with QVB. So it allows us, in order for electrons to go straight through, they have to be traveling at a speed that is equal to the electric field divided by the magnetic field. So that's called the velocity selector formula. So being able to manipulate the electric and the magnetic field allows us to determine the speed of the electrons that are traveling through that. Now there is another step. So if we look at when we turn off the electric field, now again there's only that magnetic. So once we know the speed of these electrons, formula is the electric field over the magnetic field, then we turn off that electric field again. So we have these electrons traveling through force, and we know that charged particles moving through a magnetic field will start to turn in a circle. Now maybe it's not a perfect circle, but it starts to turn in a circle due to the magnetic force. And because it's moving in a circle, that's the same as, we can call it the centripetal force. So we have QVB is equal to mv squared over r. That's where this velocity selector, that first step, was important for Thompson's experiment, because when they go through undeflected, we can determine how fast they're going based off of measuring the electric and magnetic field. If we then turn off the electric field and they turn in a circle, they're still traveling at the same speed. So we have that speed, and we can find out the charge to mass ratio by rearranging this. So Q over M is the charge to mass ratio for those particles, and that's equal to V over the magnetic field times the radius that it takes. And you could determine that based off of where it hits on the screen and then find that out. So this was the charge to mass ratio equation, and this is what we could use to calculate the charge to mass ratio of that electron. And you'll have some practice questions this week where you're dealing with that type of selector relationship. Now, based off of that work, he came to some conclusions. First, that charge to mass ratio was thousands of times bigger than something that anyone had measured for something like a hydrogen ion. So this meant that cathode rays were super concentrated charged. So there was a lot of charge in a relatively small mass, which was something they hadn't seen before. So this was actually the first time that they had observed an electron and what the nature of the electron was. So what they did then is Thompson needed to take this and put it into a working atomic model. We call it the plum pudding model or the chocolate chip cookie model. If you look down at the bottom here, it looks like a chocolate chip cookie. So he knew those electrons were bits that were able to be broken off. He also knew that there must be some positive substance because there was neutral atoms or positively charged things. So he built this type of model where these electrons are just in a positive framework. Now, the evidence for this model were cathode rays, because we knew that we could break off those electrons, those chocolate chips or those plums, and those were what cathode rays were, and we could determine the nature of those negative particles with a lot of charge and a small mass. Now, there was some evidence against this, though. If you think about this model, one is the law of opposite charges. So that's one one reason against it. The other is, how did those electrons stay in place? There's no reason why those electrons should just be locked in there. They should be attracted to that positive space or repelled by the electrons. And there's no reason why they should just be kind of locked in and glued in there. So there were some flaws with this model, but it was the start. It was the first time that we actually had a small particle, the electron, that could actually be separated. The billiard ball model was inseparable. It was just this small atom. But now we actually had negative bits that could be broken off of this. Then one of J.J. Thompson's students, he was kind of a student, so Ernest Rutherford worked in his lab, along with another guy we'll see later, Niels Bohr. He did an experiment using alpha particles. So alpha particles are a helium nuclei. So it's 2 protons and 2 neutrons. That is what an alpha particle is. Sometimes we just say it's that helium, a helium 2+ ion, or we can use the Roman symbol. But he took these and he shot them at a piece of thin metal gold foil. So he shot them at this gold foil, and what he thought was, well, if J.J. Thompson's experiment was correct, so the prediction was that most of these charges should go just straight through because that positive framework is so weak. So the prediction was that these particles should go through undeflected. And most of them did. So when they looked at the results at the screen, most of the alpha particles did pass straight through that gold foil. However, every once in a while, one would be deflected, or it would be even more amazingly bounce straight back. Rutherford, when he saw this, said it was almost as incredible as if he had fired a shell, like a large elephant shell, at a piece of tissue paper, and it came back and hit you. So he was amazed at the ones that were actually deflected. So some deflected at an angle, some straight back. From that, he was able to determine that the positive charge was in a relatively small area. So it was very dense and very positive in a small area. So he had discovered the nucleus of the atom. That was what he inferred. So he inferred that these electrons were around it. So they were whizzing around kind of like planets. But that positive charge was very dense and concentrated in the middle. Most of the atom was empty space. That was supported by this idea that most of these alpha particles went straight through. But there was a region of very dense positive charge, and that is why these alpha particles deflected. So he came up with what we call the planetary model. So this was taking these electrons, which were discovered in cathode rays by J.J. Thompson. He put them in orbits around this dense, positively charged nucleus. Now, as soon as this model was published, though, there was a serious flaw, and the one that we've learned about is Maxwell's theory of electromagnetic radiation, and that's that any accelerating charge will create EMR. So these electrons are charged, and they're moving in a circle, which is a form of acceleration. So what should happen in this model is those electrons would give off more and more energy as they spiral, and as they give off that energy, they would lose energy. So they would spiral into the center of the, and that would be it. So that model, it didn't work. We needed to revise it. And that's when another student of J.J. Thompson, Niels Bohr, came along, and he came up with Bohr's model and the first kind of quantum model of the atom. So he was able to take two different ideas to come up with his. One is Rutherford's planetary model. So there was a positive nucleus and there were negative electrons. The other was the idea of discrete energies, and he combined them into one idea. So he said that the electrons don't spiral into new orbits like the planetary model would suggest, but said that they jumped, and that there were only very particular orbits where they could exist, and he said that as governed by Planck's constant. So he was taking this E equals hf and combining it with this idea of the atomic model. So this was kind of, if you think back to Science 10 when he drew those onions model, it kind of expressed the atom as an onion where electrons could exist at these different energy levels, and if they're there, they were stable. If they went up or down, then they would emit or absorb EMR, but they would be stable at those specific levels. Now, this was something that we had actually observed, and we're going to just talk briefly about emission spectra and how that was good evidence for Bohr's model and why his model kind of worked to explain this. So we have three types of spectra. We have a continuous spectra, we have an emission spectra, which is black with very bright bands, and we have an absorption spectra, which is a continuous spectra with dark bands missing. Now, when we look at a continuous spectrum, we just observe the whole spectrum, Roy G. Biv. Now, one way where this is formed is black body radiation. So if we think about the spectrum coming from the center of our sun, we have charges, so we have electrons and things that are oscillating back and forth, so they're vibrating. As they vibrate, they give off kind of the full spectrum of light as they oscillate back and forth, and we get ever and ever increasing amounts of energy. So that's the continuous spectrum that we get. We observe it as white light because we have all these different photons of light coming from that vibration. So that's a continuous spectrum. Now, the two that are really good for Bohr's model of the atom are an emission spectrum, which we observe just bright bands, and also an absorption spectrum. So we observe bright bands in what's called an emission spectrum. To get this, we excite a gas. One example of this is like if you think about the gym, we have these mercury vapor lamps. So inside it are different gases, and they put electricity in there. Those gases get excited, and then we get these different colors that are emitted. When we look at it, maybe it appears to be only one color, but it's a whole bunch that our eyes interpreting as white. Neon signs are another example of an emission spectrum, and those ones are maybe a better example because you can see like the orange. There's a lot of reds and oranges and yellows bands being emitted that our eye sees as that one color. If we think about what's happening and how Bohr's model helps to support this idea, so we have these two energy levels. So this is n equals 1. This is the second energy level. What happens is as we excite those electrons jump up. They're excited. Now, those electrons can't stay excited forever, so those electrons fall down. And as those excited electrons fall down, they give off very specific wavelengths of light. That's what we see as these bright bands. We see the change in energy level being emitted as a single emission line. Now, an absorption spectrum is the opposite. So we see dark bands, things missing from a continuous spectrum. In an emission spectrum, we excite a gas. In an absorption spectrum, we take a continuous spectrum from white light and we pass it through a cool gas. And in this process, so we have our two energy levels, n equals 1 and n equals 2. So when we think about the absorption spectrum, we have electrons here. We have white light coming in. I'll draw it as black, but this is all the wavelengths coming in. Now those electrons will absorb that energy and jump up. But only specific amounts of energy will be absorbed. So the light that we get emitted is the continuous spectrum, except with this certain energy of light that has been absorbed from that continuous spectrum. That's an absorption spectrum. If we were to look at the sun, and if you Google Fraunhofer lines, you'll see these Fraunhofer lines which we see from the sun. We have a continuous spectrum produced in the center of the sun, but the sun has a cooler, I'm doing quotations with my fingers, a cooler atmosphere which absorbs specific frequencies, and also there's these frequencies from the earth which absorb specific frequencies as well. So if you could look at the sun and separate it out with a very good diffraction grating, you would actually see these dark bands where you could determine, okay, this is the element in the Earth's atmosphere, this is elemental hydrogen absorbing this around the sun and the sun's atmosphere. You would see these dark bands missing. Now we can kind of look at this in kind of a question context. So here we have an energy level diagram. If we have an electron, I guess we can look at the specific frequencies we can get. We can have electrons fall from 4 to 1, or 4 to 3, 4 to 2, or 4 to 3. We can get 3 different energies of photons being produced there. We can also have electrons fall from 3 to 2, or 3 to 1, or from 2 to 1. So there's 6 different energies that we could have emitted from this. If we were to look at the emission spectrum of this atom, we would probably see 6 bands, which would correspond with these 6 different energy changes, and the ones that are more probable would be brighter. Now we could also, so let's look at the energy. So if we look at from 3 to 1, that change in energy is 13.6 minus 1.5 is 12.1 electron volts. E is equal to HF, or I guess it wants wavelength, H times C over lambda. So we could find the wavelength of light that's emitted, HC over E. So we have, because it's electron volts, we'll use the 4.14. So 4.14 times 10 to the negative 15 times 3 times 10 to the 8 divided by 12.1 electron volts. So this frequency of light would be 103 nanometers if it fell from 3 to 1, which probably wouldn't be easy to see unless you're a mantis shrimp and can see ultraviolet. So that's kind of if we think about these models,